Good afternoon. Welcome to the SQAB preeminent tutorials. My name is Philip Heinlein. You don't believe that? I'll prove it. But it's not Phil or me the story is about, it's choice. Now, this is a tutorial for undergraduates. The same way the Feynman Lectures was a book of lectures for undergraduates. What's nice about Billy is that I think he's going to have a nice ramp for us of some of the most interesting problems in the analysis of behavior. Ones that captured my attention as a graduate student at Harvard when choice was in the air and Billy sort of seemed to have a handle on things. Bernstein put two keys in the pigeon box, much too scared to say, and found some relatively orderly relationships. I think it was not until Billy decided, look, let's take a general look at and put them in double log coordinates, that true orderliness of them emerged. And there's the kind of orderliness that Mike is and others have been pursuing and using as a tool through the time. Billy is interested in choice not only intertemporally and not only interspatially between two keys. He's the man that put pigeon hoppers in his attic and let free-flying pigeons come in and eat from the hoppers. So he's interested in contact with the contingencies in the real world. He's also interested in another kind of choice, not concurrent operands, but ones where animals negotiate crowding between two hoppers, and has introduced recently, he and his students, the ideal free distribution. Another nice phenomenon of choice. So what you'll hear today is not like concurrent, schedules, matching, ho-hum. What you're going to get is the tip, and I suspect a lot more of an iceberg. Well, look, number one, what am I saying? Free will versus determinism. There's more to choice than meets the eye. Billy's going to give it to us. Billy Baum.
I'm going to talk about some general issues of choice in our culture and in behavior analysis, and then I'm going to talk about the concept of behavioral patterns, these which are sometimes just commonplace in our experience, but also can be used technically in a science of behavior. And then finally, I'm going to talk about research and theory about choice in behavior analysis. So, if you think about your associations with the word choice, I think you'll see right off that in our culture, free choice is considered very important. In the judiciary, we decide whether to punish someone or not if they did something of their own free will, and if they didn't, we don't punish them. In politics, free choice in elections is considered important. In economics, free choice of consumers among goods. And at the same time, we do recognize environmental influence. We're not perfectly free because we are open to influence like persuasion, coercion sometimes, and manipulation. And this is our way of recognizing that the environment does affect our behavior. And behavior analysis focuses on that control by the environment. It assumes determinism. In our culture, people get nervous when you talk about control. In the movies and TV, we see a lot of images, of zombies and various sorts of entities that may enter a person, and then of course the person comes under control of that thing, and this expresses fear, I think, but they're all sort of fanciful fears. On the other hand, we do have legitimate fears, I think, about control. After all, we fear coercion, manipulation, bribing, withholding of goods, these instances in which someone else controls our behavior, but for their good, not for ours. These examples imply control, but they also suggest that certain kinds of control are undesirable. On the other hand, there are acceptable forms of control too, as when a parent controls a child, or a teacher, a student, a coach, an athlete. And so it's this kind of control that behavior analysis focuses on, acceptable or unacceptable. And I want you to understand that control, the concept of control in behavior analysis, is not like the flipping of a light switch off and on. It's not a question of momentary causes. Rather, the control is more like what you see in a heating system. Take a simple example like this, in which we have a thermostat controlling a furnace. And the thermostat is set to a certain temperature. It controls the furnace controls room temperature, and so the system can be said to control itself. Of course, the thing we're most interested in is the room temperature. What we see when we look at a furnace, a heating system this way, is not something that we recognize at any particular moment, but rather a pattern of, you can see here, temperature going down, and then up, down, and then up. That is to say, deviation from the setting, and then correction, and deviation and correction. And this is a pattern that we can predict from our understanding of the heating system. And what I want to introduce is the idea of patterns of behavior of organisms, not just of heating systems. And we recognize patterns of behavior all the time, I think. We predict behavior from other behavior. This is what it is, I think, to know a person. If I know someone, I can predict their behavior. I know that Peter, when he gets ready for a convention, he brings along transparencies and felt-tip pens, and he writes on them all the time. And I also know from Peter's past behavior that he tends to be sort of helpful person. And I also know that he doesn't shrink from attracting attention to himself. So when a speaker expresses the wish that he had something to write and display with, why, Peter, I can predict that Peter will supply a transparency and a felt-tip pen. And this is what it is, I think, to know someone. Psychologists, personality psychologists, do this sort of thing all the time when they study things like self-esteem, intelligence, suicidal tendency. They're trying to predict behavior from behavior. They do some kind of observation. It may be a paper and pencil test, but then they go on to try to predict behavior. Now, what this tells us is that behavior can be seen as organized into patterns, that actions naturally fall together into categories, we could say. Take, for example, the statement, John loves Sally. Now, what does this mean? Well, there are various things that John does, and when we see some of those things, we start to say, well, John loves Sally. You know, he talks about her all the time. He calls her on the phone, takes her out, buys her presents. And when we see a whole bunch of these kinds of actions, we start to say, well, John loves Sally. And moreover, we can predict this, some of these, from others, right? I mean, if we see that he does, say, 1 through 6, well, then we start to suspect he probably is also writing poetry to her. So these various actions all fall together into a category, John loves Sally. And when we see a collection of actions like this, we can also start to talk about it as a population. Now, a population of organisms is perhaps the easiest thing to start thinking about. We could be talking about the mice that live in a meadow. And there might be, let's say, different degrees of coloration among the mice. There might be, say, 4 different types. And I've labeled them here A, B, C, and D. So you could think of this circle here as the meadow, and then we have types A, B, and C. And they do not occur in equal frequencies. You can see that type B is the most frequent, and the other types are less frequent. Type A is the least frequent. And this is a population of organisms distributed in space. Now, the difference between a population of organisms and a population of behavior types, or response types, or activities, if you like, is that the behavior types are distributed in time rather than in space. But that is actually the only difference as far as I can see. You could be talking here about an observation of behavior. Maybe there are 4 different activities or 4 different ways of getting a job done. And this is an individual organism, and we see that as with the population of organisms, this type B, response type B, is the most frequent in the behavior of this organism. And type C is less. Type A is the least frequent. And so what we see here is not something that can be observed at any moment in time, but has to be observed over a period of time, but is a recognizable pattern, a pattern of frequencies in this case. And every population is associated with a pattern of frequencies like this. That's the nature of a population. Now, what I'd like to introduce you to is the idea that choice consists of such a pattern of behavior. That is the way behavior analysts think about choice. Well, research on choice involves usually simple experiments. The whole idea is to try to simplify and to study these things in the laboratory with a variety of organisms, often enough pigeons, rats, monkeys, sometimes people. And the way of thinking about this is that it's a problem of obtaining resources at multiple sites. That is to say, getting the things that are important to you, but there may be more than one way of getting those things, or more than one place to get the things that are important. We could be talking about a situation, let's say, where there were different ways of getting the same resource, food, you might get at home, in a restaurant, at a friend's house, a parking place. I hunt in one lot and then in another parking lot. If you're searching for a mate, you might find a mate in a class, in the library, at a bar. If we're talking about different resources, why it might be a choice between, say, food and sex, or which do you prefer at the moment, or between Italian restaurants and Chinese restaurants. And the way that behavior analysts study this kind of problem, obtaining resources at multiple sites, is with what are called concurrent schedules. And here's a diagram of a simple example. And suppose that we were working with pigeons. Why, these would be two response keys. If it were a person, it might be two buttons they could push. And each one is associated with a payoff schedule. And the payoff schedule allows responses at the two alternatives to operate a reinforcement dispenser. And reinforcement might consist of money or cigarettes or heroin or food. And so what you have is, in this case, just two alternative ways of obtaining the same resource. A common result in experiments of this type is what's known as the matching law, in which a pattern of behavior, the ratio of responses at the two alternatives, tends to track the reinforcement ratio, the ratio of the payoffs at the two alternatives. And here you can see some actual data, and they fit pretty well to this line. So what this says, for example, is that if there were 3 times as many reinforcers delivered on the left key, then behavior would roughly tend to a pattern of 3 times as many responses on the left key as on the right key. And then if you switched it, let's say on the right key there were 5 times as many payoffs, then the behavior would also shift and would be distributed. You'd see a pattern of roughly 5 responses on 5 times as many responses on the right as on the left. And this is expressed in this equation here, that the ratio of behavior tends to equal the ratio of reinforcement. Now, this matching law is of great interest to behavior analysts, and I'll come to a moment to how theories of choice attempt to explain it. But first, I just want to make note, I'm not going to talk about this other line of research, but there is another line of research in choice called Selfcontrol, and it focuses on choices that have to do with time horizon, that have to do with getting some small satisfaction immediately versus something much more important in the long run, like junk food versus eating vegetables. Junk food tastes nice in the short run, but in the long run it's really much better to eat vegetables because of your health. And of course a choice like studying versus socializing. Socializing is fun in the short run, but studying may be much more important in the long run. To return to choice and the matching law, there have been various theories put forward to explain the kinds of choice phenomena that we see in the laboratory. All of these theories involve the notion of optimality. and optimal patterns of behavior. So I want to make sure that we understand this idea of optimality clearly. If let's say there were 4 alternatives, 4 ways that you could behave, A, B, C, and D, and one of them pays off better than all the rest, then the optimal thing to do is to choose that one. Optimality is the development of patterns that approach the best possible. And it makes certain assumptions. In particular, it assumes that there is a currency, that is some variable, some feature of the environment that is to be maximized. Like that could be money. It could also be food. Getting the most money, earning the most food, that would be the currency. And the other important assumption in optimality is that behavior affects the currency, that there is a contingency by which behavior can manipulate the currency. If you look at the lower diagram here, we go from a situation in which there are 4 discrete alternatives to one in which behavior can vary continuously. And I bring this one in particularly to help you to think about frequency of behavior, that is the pattern. You may have a wide range of possible patterns. One of them may be best. In this diagram, this one here is the best, and it has the highest rate of payoff. So that would be the optimal pattern. And the prediction of optimality theory is always that behavioral patterns move to those that maximize the currency. Now I'm going to talk about 2 theories. The first one I'll call the good switching theory. It's known as melioration among behavior analysts. It focuses on when you should, or when an organism should switch from one alternative to another. It focuses on short-term changes in value. The basic idea involved is if you are spending your time at one alternative and then another one becomes higher in value as time goes by, you should switch to the one that's higher in value. And that is what makes melioration an optimality theory, that always it says switch to the better alternative. There are 3 different kinds of circumstances in which you get these local changes in value that make this good switching theory a sensible idea. The 3 types are satiation, depletion, and interval scheduling. Now, satiation should be easy to understand. The more pretzels you eat, the less pretzels you want. And so the value of eating pretzels goes down as you eat more and more pretzels. And if there's a bowl of peanuts by, which is the constantly available alternative here, eventually the value of eating pretzels reaches and drops below the value of eating the peanuts, and at that point you should switch to eating peanuts because it's the more valuable alternative. With depletion, it's the same kind of thing. If you've ever gone berry picking, you know about depletion. You come to a bush There's a lot of berries on the bush. You pick there for a while. The more you pick, the fewer berries there are, and pretty soon you're having a hard time finding any more berries. Well, there's another bush. It's a bit of a hike, but it's over there, and so at a certain point, the value of staying at this bush must drop below the alternative, the other bush, and you switch. And you go over and you start picking at the other bush. Now, interval scheduling is a situation in which there's some factor that's out of your control. You don't have any control over the mail carrier. Now, if you wait 2 weeks, let's say, before checking your mail, it's a pretty good bet there'll be some mail in your mailbox. You can check it more often. But if you check it more and more often, you're not going to get mail more often than 6 times a week. That's the nature of an interval schedule, that there is some factor that's out of your control, and therefore it pays to wait. As time goes by, the alternative becomes more valuable in the sense that it's more likely to pay off. Now, what happens when you begin to choose an interval schedule at the very beginning, if you haven't worked out, haven't been there for a while, haven't done that thing for a while, it's very likely to pay off. But then it immediately switches down, you see, and you get all that mail if you haven't checked it for 2 weeks. But then after that, you keep on checking your mail. You're only going to get it 6 times a week. And on the other hand, there's some alternative, let's say, which is also an interval type of schedule. Well, you're ignoring it. It's getting better, that means. And in this case, notice it's the alternative that's getting better that causes the crossing over here. And at the point where it does cross over, it makes sense to switch. So that's the good switching theory, melioration. And the important point about melioration is that the switching always tends to equalize the values of the alternatives. And this is how it explains the matching law by this equalizing of value. Now, a second type of theory of choice is long-range optimizing. And here I think it's intuitively quite straightforward, because it's a matter of thinking about different patterns of choice and their associated payoffs. And the idea would be that choice will move toward a pattern, a distribution, relative frequencies that will maximize the overall rate of reinforcement, the overall satisfaction that is produced not by any one of them, but by the whole mix. And so we have these two different theories, one of them tending to focus on more short-term switching between alternatives. The other one is more long-term in the sense that it involves these patterns through time and the pattern moving toward, in the long run, an overall maximizing of satisfaction. The kinds of experiments that behavior analysts do on this, as I said before, involve concurrent schedules. And a popular situation to study has been concurrent interval schedules. Variable interval schedules are ones in which the intervals vary unpredictably from time to time, but the idea is always that time has to go by before a reinforcer can be obtained, and so there are always these time-limited schedules. If you have a pair of such schedules, and let's say here there's a 4-to-1 difference in their potential payoff. One of them, let's say, can pay off as much as 80 times an hour. The other one can pay off 20 times an hour potentially. We can look here at the pattern of choice between the two alternatives. If the organism puts all of its behavior onto the lean alternative, then potentially it can get only 20 reinforcers per hour. If it puts 100% of its behavior onto the rich alternative, then potentially it can get 80 per hour. But if it distributes its behavior between the two, then potentially it can get 100 per hour. It may not actually get 100 per hour because in order to do that, you would have to be on the spot all the time, every time a reinforcer is set up. But the important point to see here is that matching would predict that 80% of the responses should go to the rich alternative, 20% to the leaner alternative, and that's what melioration predicts. Well, it happens it's also what long-range optimizing predicts too, because the maximum overall rate of reinforcement is obtained with that distribution of 80% to the rich and 20% to the lean. So that pattern is the optimal pattern for concurrent variable interval schedules. All right, well, that's not so interesting because it doesn't help us to decide between the two theories. They both predict the same thing. A situation in which the two theories make different predictions is the situation in, again, concurrent schedules, but one in which one alternative is a variable interval schedule and the other alternative is a variable ratio schedule. Now, a variable ratio schedule is like a gambling situation. Every response has a certain probability of paying off. And it should be your intuition that the more you work at such a schedule, the more payoff you get. And in fact, if you think about it, it should be the case that the payoffs are directly proportional to the amount of work that you put into it. And so you should, if you think about it like that, you should be putting a lot of your choices, a lot of your behavior onto that ratio schedule. And both melioration and long-range optimizing predict a preference toward the variable ratio schedule. I want you to notice that this axis actually begins at 50% and goes up to 100% choice of the ratio schedule. I have made the assumption that there's a constant rate of responding on the ratio schedule. But now let's look at these as a choice. We have potential of 20 per hour reinforcers on the interval alternative, and then there's a probability of payoff of 1/80th for the ratio alternative, which means that it'll take about, on average, 80 responses to get a payoff. The melioration predicts, because matching occurs right about here at about 77% of choice for the ratio schedule, that there'll be a preference, but not nearly so strong as what the long-range optimizing theory predicts. The optimal distribution here, the optimal pattern of behavior, is about 94% in favor of the ratio schedule. So where melioration always predicts matching, in this case, long-range optimizing predicts actually deviations from the matching law. initially, research on this type of situation, concurrent variable interval, variable ratio schedules, seemed to support amelioration because it was found several times over that you obtained matching in this situation. Subsequent research has shown that this is not quite the final answer, because it turns out that if you give organisms a lot of experience with this type of situation, they tend toward the long-range optimizing solution, and particularly if you give them guidance. For example, if you give a pigeon a light that tells it now you are behaving optimally in long range, then it seems they get to be quite good at long-range optimizing. So this is not a final answer to the question, but it appears it's not an open and shut case that amelioration is right and long-range optimizing is wrong. Perhaps actually quite the reverse is true, that under optimal circumstances, long-range optimizing occurs. So what I hope you will have gotten out of this is, first of all, that there's no reason to be frightened of the word control, that behavior analysis is based on control, but it's not a question of zombies and body snatchers. And I hope that you will have learned also that choice can be thought of as not a momentary kind of an event, but rather as a pattern of behavior through time, and that behavior analysts have done a variety of experiments and come up with a variety of theories that we find very interesting to talk about choice.
There's a lot more that could be said, but let's do it in response to some questions if you have them. And this is a tutorial, so feel free to ask questions over the range of simple to complex. A billion will handle them all.
Of course, if you have questions, you should consult your instructor.
John?
Are there differences between humans and animals and the extent to which they conform to the matching law?
Well, if you do a broad survey of the research on humans and animals, and you're not selective about it, it appears that humans are not as good as animals, as subjects for this research. But it may be that it's just more methodologically challenging to work with people. It's often difficult to create a situation that's compelling enough for subjects. Actually, there are a couple of my students here, John Kraft and Leanne Millender. I don't see Leanne, but I do see John, who are working with groups of people now, under UNH undergraduates, of course, and it's very easy to bore undergraduates. So you do need to try to find ways to keep them engaged. And it turns out that, by and large, if you offer money prizes and you make the situation competitive, it becomes very compelling. And Leanne was telling me about that she was afraid that her subjects were going to start exchanging blows in her panhandling experiment, because they were panhandling for tokens, which then if the person who got the most tokens would get a monetary prize, and so that got them really interested. I did an experiment myself some years back, before the days of video games, in which I actually tried to create something very like a video game, and I got some good data that way. Telling people they were destroying spaceships, that sort of thing. So I think the answer is it can be done with people. It is easier to do with animals, non-human species.
Can you tell me how you derive the matching predictions for the concurrent VI-VR when the obtained reinforcement rate on the VR depends on how fast they're responding? Because on the concurrent VI, you can just use the scheduled reinforcement rates, because for almost any response rate, that's what the reinforcement rate will be. But how do you derive the matching predictions when the VR depends so much on the responses that are...
Well, in order to make that slide, I just assumed a constant response rate of 100 responses per minute. But actually what you can do is you can simply write out the equation for summing the two feedback functions, and then use partial derivatives. So it's actually a straightforward problem, but you're right that you have to in some way take account of the actual rate of responding on the ratio schedule.
Peter. Matching is an amazing phenomenon because it can be explained both on a molecular level, or attempts can be made to explain it on a molecular or a molar level. I've always liked amelioration because it said, at any moment, just switch to what's best. And presumably the animal could be conditioned so that I'm doing this for a while. All of a sudden, the value or the attractiveness, the conditioned reinforcement value of the alternative, as you nicely showed, it increases over time. So I was a little dismayed to hear the latest news that we had moved away from the matching amelioration resolution of this issue towards the optimum. How do we get animals to optimize? Is it possible to do it with local molecular mechanisms, or does that require a different approach to choice?
Well, of course, I don't think it's possible to do it with local mechanisms, because it implies a sensitivity to patterns of behavior and overall payoffs that cannot be evaluated at a moment or even in a short period of time, but rather over some range of time. And so it's a challenging problem for any organism, I think. It's a question of sort of broadening your horizons, and that's not always easy, particularly I think for pigeons, So apparently the tendency will be toward some more short-term kind of a strategy like melioration, but if you can find a way to get over the problem of sensitivity to the long range, then it seems that organisms, even as humble as rats and pigeons, and for that matter, people are not always good at long-range optimizing by any means, but under the right circumstances, with experience and with instruction, they start to move in that direction. And in a way, I suppose that shouldn't be too surprising, because if you could optimize, if you could somehow or other figure out to do it, why would you, settle for less?
Well, I'm afraid we're out of time. We don't have to settle for less. We can have the whole cake. Dr. Baum will be around to answer a few more questions that you can ask in the privacy of one-on-one or several-on-one with him after today's session. The basics are simple. At least listening to Bill, he made them seem simple, and that was a marvelous feat. But it gets as complicated as you want, as Paul's question pointed out. So there's a lot of possibilities here to do things that are important and interesting and challenging, and I very much appreciate Bill's introduction.